Hi everyone, Christy here, and we're ready for week 2. We're going into module 2, and we're going to be talking about motion in 2 dimensions. So we're going to continue with some of the equations we used last week, actually all of them, but we're going to apply them to motion in 2 dimensions. So those wonderful movies that we watched, the Rube Goldberg machine, we tried to pick out some simple motion, linear motion, so that we could talk about only motion in a straight line. So motion only, say, in the horizontal, or motion only, say, in the vertical, in the Y. But, of course, in real life, we all know that motion is more complicated than that. So this week, we're going to do some problems for motion in 2 dimensions. We have to remember what we learned last week. But we're going to learn a few tricks to learn how to use a little simple math so that we can separate out the components of motion. What do I mean by that? For example, this if you look at a cannonball, shooting a cannonball off, cannonball comes out and it goes in an arch. So it's not moving just in a straight line, not just horizontally, or we might call that the X direction. It's not moving just vertically, falling down in the Y direction. It's moving in both directions. It actually goes up in the Y direction a little and then starts to come down in the Y direction. At the same time period, it's also moving horizontally, so in the X direction. So how do we deal with that? We're about to look. So you're saying to yourself, wait, what did I get myself into? Physics is bad enough, but I've got to remember geometry and trigonometry. Some of you may not even have had trigonometry, but don't worry about it. It's not that hard. It has something to do with nifty little things called right angles. So first thing we're going to talk about is coordinate system. So we're talking about motion. We're talking about something moving in the north, the south, the east, or the west direction. So when we're applying this in physics, we're going to assign this type of motion to a coordinate XY system. So we'll talk about that for a minute. Then we're going to talk about the math that we need to be able to separate out the components of two-dimensional motion. And it's math, basically, of right angles. So what do I mean by right angles? I mean, for example, this angle is a right angle because remember right here, that's two perpendicular lines and that's a 90-degree angle. That's the definition of a right angle. So we're going to look at some math that applies to those right angles. The first mathematical theorem that we're going to look at is the Pythagorean theorem. And then we're going to look at 3 simple trig functions that help us deal with that angle. So let's go ahead and get started. So first of all, let's apply the coordinate system. So you guys are probably all familiar with the compass, and compasses or compass system have north, south, west, and east. When I was in school, I had a teacher that told me nose, shoes. So nose is north, shoes is south, and we, so west and east. And then over here, we've got our little right triangle that we're going to be talking about we've labeled the sides A, B, and C. And then we have an angle here that we're designating as theta. So how do we apply a coordinate system here? Well, it's pretty simple. You just put the direction. Usually what we try to do is make things simple on us, and the beginning of the motion we're talking about, we try to put it at the center of an axis system. So here, our north here, we're actually talking about this is the y-axis. So here we'd say this is positive y. So north is positive y. We can refer to this as negative y. Okay, the horizontal is the x-axis. So over here, if we're headed east, we're headed in a positive x direction. And if we're headed west, we're headed in a negative x direction. Now this is arbitrary, but it's typically what we use in physics, so it's what your textbook uses, so I just wanted to show you that. Okay. So first of all, the Pythagorean theorem applies to right angles, and you're probably, most of you, familiar with this. It's we're talking about, in this problem that we're about to do, displacement along the hypotenuse of a right triangle. And I'll show you what I mean with a specific example in a second. So here is just plain old right triangle. We're calling this side A, this side B, this side C, and this is the angle theta. So here we have a squared plus b squared equals c squared. So if I know the length of A and I square it, and I add to that the length of b squared, then I will get the length of c squared. So the hypotenuse, we can use this handy equation to convert between A, B, and C in a right triangle only. Okay, and we're going to use right triangles this week. So let's look over here after we put our coordinate system on. And so now we're applying this to physics, not just a regular old triangle. So it's the same thing though. Instead of A, we've got Y. And here we're talking about a change in y. That's what this delta means. Greek delta means a change in y. So going from 0y up to some positive value of y is a change in y. Here we've got a change in x. So going from 0x, motion in this direction, to some positive value of x. And we're going to call the hypotenuse the displacement here. It's not the distance, it's the displacement. Can be the same as the distance, and it will be in the problem we're about to do, but it's the displacement. So the hypotenuse is there. So let's look at an example of a problem where we can use it. So let's say that you're feeling very energetic. You go to Egypt and you're going to climb up one of the Great Pyramids. If the height of the pyramid, okay, so over here I have a pyramid labeled, and I've drawn a line here. So the height from in the center to the top is 136 meters from the ground to the very top of it. And the width of the whole base of the pyramid is 230 meters. And you're hiking up this side, you're climbing up the side, any of the sides of the pyramid. We want to know what's the magnitude of the displacement from your original position. So if we take this pyramid and we're going to make it into a right triangle, so we're just going to take half of it. So over here, this is our right triangle. So I've just taken this half of it, and we're putting our starting position here at 0, 0 in our XY axis. We've got our height here is our change in y, so 136 meters. Our width is not the width of the entire pyramid, because we're only taking half of it, so 115 is half of 230. So we've got two sides of our right triangle, 136 and 115. So that's our A and our B. So this is our C, or our D, right, our hypotenuse, and we can solve for that. So here's the equation. I've written it the other way, which doesn't matter. So to solve for that, you just plug in those values. You've got to square each one of them. After you square 115, you add 136 squared to that, and then you get that answer and take the square root of it. You should get 178 meters. So 178 meters is the displacement that you make. So that's how far you go from your original position at the bottom to get to the top, 178 meters. That's the magnitude of your displacement. Now, it doesn't tell us anything about this angle. Okay, so now we want to know what is the direction. So how do we deal with the direction? So we got to use something a little different. We got to use trigonometry. It's very simple trigonometry. We're not getting too fancy with this, but we know the magnitude. So we just got the magnitude is 178 meters. We can find out the direction. So we need what the direction is going to be this angle. So kind of from the picture, we know we're going kind of north and east. So we're going in the northeast direction, but we don't know what angle we're going up. Is it a really steep pyramid? Is it a really low slope pyramid? We don't know, but we have some formulas that we can use. Now, if you've taken trig, then you might remember sine, cosine, and tangent. Okay, so if I want to know, I have a relationship that is the ratio of two sides of a right triangle. So if I have my triangle, okay, and whatever that angle is, okay, the opposite angle of that triangle is called O, or the opposite. Okay, so I'm calling it O or H. So that's opposite. So see how the Y here is opposite? The hypotenuse is H, which is the D here. Okay, and then this side, which is the X, which is the X value, is the adjacent. So we've got opposite, adjacent. So we're talking about adjacent to this angle. Yeah, hypotenuse is also adjacent, but it's the hypotenuse. It's the one that's across from the right angle. So the other one that's next to it is the adjacent, and the one that's directly across from it is the opposite. Okay, so sine theta is equal to opposite divided by hypotenuse. Cosine theta is equal to adjacent divided by hypotenuse. And tangent theta is equal to opposite divided by adjacent. Now, there's a mnemonic that I learned a million years ago that I'll never forget. There are other mnemonics too, but I'll always remember this. Oscar had a heap of apples. If you remember that sentence, Oscar had a heap of apples, and you know it goes sine, cosine, tangent, you'll never forget. Sine is O over H, Oscar had. Cosine is A over H, A heap, and tangent is O over A of apples. So that's just an easy, silly way to remember it, but I have a PhD and I still remember it that way. So now what we need to do is we need to actually figure out what's going to help us. So we're looking for, we have the magnitude of the displacement, so we actually have all of these sides, and we want to know theta. So we could really choose any of these to solve for it. But let's look at tangent theta. Okay, so opposite, these were the values that we were given originally, and we could calculate theta without having to know what the displacement is at all, or the hypotenuse. So this is independent of that calculation. So if we take this value of the opposite, which is 136, we divide it by the value of the adjacent, which is 115, then we can say that it equals to the tangent theta. Now you need to look at your scientific calculator, and you'll have to use the inverse tangent. So you say theta equals the inverse tangent of 136 over 115, and you get 49.8. I want everyone to get your calculator, pause the video, and see if you can figure out how to get that number so that you know what you're doing. Okay, make sure your calculator is in degrees, okay, because these are degrees. Usually inverse function is a second function and tangent, but you'll have to look depending on what model your calculator is. So on your climb up the pyramid, the magnitude of your displacement vector has a magnitude of 178 meters at an angle of 49.8 degrees from the horizontal in the positive x direction. Or you could say 178 meters at 49.8 degrees northeast. So I hope that makes sense. Let's move on to something else. So now that we have reviewed sine, cosine, and tangent for displacement, about how we can use it in problems with having to do with velocity. Okay, so if we have in this problem, so we want to find the x and y components of the velocity of a helicopter that's traveling 95 kilometers per hour, and it's going in a straight line at an angle of 35 degrees to the ground. Okay, so imagine the helicopter is starting here. We're putting it as its initial position at 0, 0, and it's moving out in a straight line at 35 degrees from the horizontal. So the horizontal is the x. So the best thing you can always do when you're solving a problem is to draw a picture, label it with what you know, what you're looking for. So we have an angle and we have our hypotenuse here. So if we have our angle and we have our hypotenuse, we can use trigonometry to find out these components of the velocity. We can find out the vertical y component and the horizontal x component. We just need to use those trig equations we were just talking about. So if we want to find out, we can write sine theta is opposite over hypotenuse. Okay, so that's y. So here's theta. We know what it is, and we'll plug that in just a second. We want to know what y is. Well, remember we said Oscar had, so opposite over hypotenuse, opposites Vy, and h is 95. So we can plug those in, and we'll get Vy over V. And here we're talking about an average speed. Okay, so average velocity is what V is. That's that 95. If we want to get the x component, we just use cosine, and we use adjacent. So it's the adjacent over the hypotenuse. So let's see what happens when we plug that in. Okay, so for the y component, we plug in sine 35 equals Vy over 95. We do a little algebra, a little manipulation here. Multiply 95 times sine 35, and you get 54 kilometers per hour. So in the y direction, so starting from 0, going up in the y direction, the component of the velocity there is 54 kilometers per hour. Now it's not distance, it's velocity. Okay, so that's the rate of change of movement in the y direction. Now let's see, what about the x component? Now we're going to use the cosine. So x component's cosine 35 equals Vx over 95. Do the same thing and you get 78 kilometers per hour. Okay, so we don't know how long this helicopter has been flying, but we know that for any given time period, think about it. Which one? Is it going to go further in the x direction or the y direction? In the x direction, right? And let's look at that specifically. So if the helicopter has moved 54 kilometers per hour velocity north and 78 kilometers per hour velocity east. So if the helicopter flew with this magnitude and direction for 15 minutes, how many land miles would the helicopter have traveled? So let's think about land miles equals distance in the x direction. So distance in the x direction. Remember that formula that we have that relates velocity, distance, and time is the average velocity is equal to delta x over delta t. So we're going to solve for delta x. So we take the average velocity, 78 kilometers per hour. We're going to multiply that by the time. We're not going to use 15 minutes because our velocity here is in hours, so we have to convert it to 0.25 hours. You multiply, and you get 19.5, but if you use the right sig figs, you get about 20 kilometers. So in the x direction, in that time period at that speed, the helicopter's gone 20 kilometers, which is about 14 miles. Okay, so now you know what I'm going to ask. What about the altitude? How high will the helicopter be? Well, we can calculate that also. So we just use that component for Vy that we got, and we're going to plug in Vy and the time, which is 0.25, so 54 kilometers per hour times 0.25 gives us 13.5 kilometers. I should have rounded that to about 14 kilometers, but it'll be about 8 miles. And so if I did my sig figs right, it'd be about 8.0 miles. But anyway, so this is how you separate out the x and the y component when you're solving for velocity. So I want you to remember this because in a lot of problems, and this one is a helicopter, but what we saw, a cannonball, we can separate those out. I also have additional videos with other problem solving for different types of problems that we're going to have this week, but it all comes back down to this. You have to be able to separate out the x and the y component and then apply those in those specific directions. So another thing you'll see is oftentimes one of those is simpler than the other, and you'll be able to do one, get the time, and then plug it in for the other. So, but there are other videos that go into detail on that. So I hope this was helpful, and I look forward to hearing your discussions this week about two-dimensional motion. Yay!